Terrible weather here on the East Coast, but out in California, the West Coast been hit by El Nino storms, which has caused a state of emergency. A rare kind of earthquake, one unlike anything recorded in modern history, silently approached the California coastline. Early risers along the shore felt an inexplicable stillness, a sense that the land itself had paused in anticipation of something vast. Fishermen noticed unusual readings on depth gauges while dock lines creaked taut at unnatural angles as if tugged by invisible hands. The Pacific breeze carried no warning, no tremor, nothing beyond an eerie quiet. Hikers in the coastal ranges reported subtle stiffness underfoot, a sensation that the contours of hills and valleys had changed overnight. Most dismissed it, attributing it to fog, fatigue, or faulty equipment. Unaware of the extraordinary event unfolding deep within the servers of the United States Geological Survey. However, the data told a radically different story, one that demanded immediate attention. Before we start, smash the like and subscribe buttons for more updates. Across California, tectonic sensors along the Pacific Plate boundary began transmitting early morning readings, revealing an abrupt vertical displacement at multiple points. At first, analysts suspected errors, glitches in calibration, or noise within the system. But offshore pressure sensors designed to detect minute water column changes confirmed the anomaly in perfect sync. The readings were unmistakable. The coastline had risen. Segments stretching hundreds of miles had experienced sudden uplift. GPS stations corroborated the elevation changes, detecting shifts that, while subtle in centimeters, were unequivocal. The USGS recognized the significance and issued a red alert, an event no coastal resident had ever expected to see. Scientists who had spent decades studying slow tectonic processes suddenly confronted something unprecedented. This was not gradual fault creep or seasonal variation. The land had moved, and it had done so in mere hours, defying the slow rhythm of tectonic stress accumulation. The implications were enormous. Across the state, experts scrambled to interpret the data. Seismologists checked for foreshocks or tremors. Geophysicists mapped the distribution of uplift. Marine geologists analyzed offshore contours for patterns. The data showed coherent, coordinated uplift rather than scattered shifts. If anything, it raised more questions than it answered. Physical changes along the coast were subtle. Beaches didn't expand, cliffs didn't rise dramatically, and roads remained intact. Yet now, tidal pools sat a little bit above the previous tide line. It felt like boat channels were narrower, and a few piers leaned more noticeably than the day before. These quiet changes suggested a dramatic subterranean adjustment. Maybe the most puzzling aspect was that the uplift occurred without seismic noise. Normally, any vertical movement of the crust is accompanied by detectable quakes, tremors, or foreshocks. All those signals bypassed this event. It supported the feeling that an unusual mechanism was operating deep beneath the surface. The Pacific Plate had shifted upward in a manner rarely documented in history. California's tectonic landscape is complex. The Pacific Plate slides past the North American Plate on a network of faults, but the San Andreas is merely the most famous. The state's geology is woven from dozens of interacting faults, some offshore and some buried. Sudden uplift indicated stress had redistributed along these deep structures. Some had speculated about subcrustal forces pushing upwards, the kind of force that can subtly realign fault zones. There was little in historical record that matched. The spatial coherence of the uplift was striking, a sweeping curve, really, hugging much of the coastline. That spoke to a unified push from beneath. Vertical movement of only mere centimeters across hundreds of miles represents a monumental geological event. The crust, normally rigid, had moved in near-perfect coherence, suggesting either a massive pressure release or that a large segment of the Pacific Plate had tilted upward. Fault realignment, lithospheric adjustments, or subcrustal deformation were all considerations. USGS red alerts are reserved for those phenomena which may have cascading effects. While the uplift caused no immediate catastrophe, the significance lay in the stress it revealed along California's margin. A shift upward suggested that the tectonic system had altered its configuration in ways that demanded scrutiny. Certainly, the more immediate implications extended into coastal dynamics. Even minor vertical adjustments may alter tidal basins, influence storm surge risk, and affect erosion. Ignore my previous message with errors in it. Groundwater flow could change, affecting aquifers. Cliffs, slopes, and other infrastructure that had been designed for one elevation now needed re-evaluation. Current models of tectonic behavior were called into question. Scientists had assumed a fairly predictable buildup of stress across California's faults. The sudden uplift proved this was not the case. Vertical motion could take place without earthquakes or volcanism. Thus long-term predictive models had to be revised. Attention turned to the offshore tectonics. The seafloor off California is riddled with hidden faults and ridges. A previously unrecognized movement on one of these oceanic faults could account for the coordinated uplift. Such offshore disturbances can have profound onshore effects on the distribution of stress and interaction among faults in complex ways. Ecological effects were subtle but significant. Tidal habitats that depend on just the right amount of water coverage experience subtle changes. Some species had to adapt to new elevations. With minimal disruption in the short term, these changes nonetheless presage longer-term impacts on intertidal and nearshore ecosystems. Deep geological forces were examined. One idea was that strain had been building up on a deep portion of the Pacific Plate and the uplift marked the release of that pressure vertically. Another focused on slow slip behavior at sea, normally subtle, but in this case possibly faster than usual or more coordinated than usual. The nature of the uplift itself was intriguing. Over hundreds of miles, the crust moved in a smooth, coherent way. A pattern seldom, if ever, seen. Most vertical displacements occur in patches. This broad sweep suggested a major tectonic structure miles beneath the surface had shifted, raising questions about its identity and behavior. Public reaction was marked by curiosity and concern. Residents wondered whether the uplift preaged larger seismic events. The USGS emphasized the alert's purpose was monitoring, not prediction of an imminent earthquake. Yet the mystery captivated public and scientific attention alike. The absence of seismic noise suggested ductile deformation deep below the brittle crust. Rock at certain depths can behave like slow-flowing material. If this had occurred, it could explain how the crust lifted without detectable earthquakes. Subsurface fluids were considered. Water, gas, or brines can alter pressure regimes within the crust. Though magma involvement seemed unlikely, fluid migration could have allowed smooth crustal movement, weakening fault zones and enabling uplift without jolts. The uplift's impact on tectonic stability remained central. The plate boundary appeared to be adjusting, seeking a new equilibrium. Whether a one-off anomaly or part of a larger pattern remained uncertain, but it offered a rare opportunity to study California's complex tectonic behavior. The USGS intensified monitoring. Satellites measured elevation changes. GPS stations streamed continuous data and offshore buoys tracked subtle variations. Past seafloor mapping helped identify areas most susceptible to vertical motion. The event highlighted the interface between human activity and slow geological processes. The uplift became a marker, a signpost in California's evolving landscape. It was neither catastrophe nor trivial occurrence, but a demonstration of the Earth's capacity to shift quietly yet profoundly, revealing dynamics invisible without precise instruments. Research vessels hundreds of miles offshore were redirected to study the anomaly. Multi-beam sonar, seafloor mapping radar, and pressure sensors offered the first direct three-dimensional images of the uplifted margin, revealing subtle yet measurable changes across the continental shelf. The ocean surface remained calm, but sonar scans showed ridges rising, troughs narrowing, and continental shelf gradients increasing. The uplift extended offshore, confirming that this was not a superficial coastal adjustment, but a margin-wide tectonic shift. Lead geophysicists observed that the uplifted landscape had the appearance of being sculpted, rather than fractured. Sediments remained intact, as if they were lifted as a whole rather than being disrupted by any kind of brittle faulting, deepening the mystery of the mechanism behind the motion. A second vessel measured slight deviations in deep currents. Although imperceptible at the surface, these shifts did indicate that water flow patterns were subtly affected by new seafloor topography, influencing sediment transport and nutrient circulation over time. The anomaly drew international attention. Scientists studying volcanic arcs, mountain building, and mantle dynamics all contributed expertise to form collaborative models to explain the unusual uplift. Japanese researchers suggested that it could be the deep mantle convection currents which are responsible for gradual reshaping of the Pacific margin until some threshold was reached that constituted a vertical adjustment. European scientists hypothesized about tectonic stress waves propagating across the Pacific from distant sources, converging on California to cause coherent uplift. Onshore, survey teams revisited high-precision GPS benchmarks. Subtle shifts of a few centimeters to more pronounced changes confirmed the offshore data, reinforcing the consistent pattern of uplift across the region. Hydrologists monitored coastal aquifers from Humboldt County to Ventura. Water tables shifted variably, reflecting changes in subsurface pressure distributions. Though immediate hazards were absent, future groundwater behavior would need careful observation. Coastal engineers evaluated infrastructure. Harbors, bridges, and tidal channels were inspected for stress or misalignment. Minor adjustments noted emphasized the importance of revisiting assumptions about stability in light of the uplift. Satellite radar interferometry produced crisp images of deformation. Waves of color revealed the geometric sweep of uplift, tracing curvature along hidden faults. Lesser-known offshore thrust faults emerged as potential contributors, distributing stress silently beneath the surface. Some researchers proposed that the uplift represented tectonic breathing, a subtle episodic stress release without violent rupture. If true, similar events would have occurred in the distant past, shaping California's coastline long before modern instrumentation existed. Atmospheric researchers incorporated elevation changes into microclimate models. Though the effect on weather was minimal, coastal fog, breezes, and temperature gradients could subtly evolve over time, influenced by the altered terrain. Residents conducted informal surveys, documenting changes to sea caves, arches, and rock shelves. Photographers noted subtle shadow variations indicating shifts in shoreline angles and reflecting the cumulative impact of uplift. Geologists hypothesized that lithospheric adjustment, not just shallow coastal faulting, might explain the event. Buoyancy imbalances could have triggered coordinated uplift, demonstrating the dynamic nature of the rigid outer shell. Oceanographers considered sea level readings. Tide gauges showed anomalies, not from ocean change, but because the land had risen. Local sea level measurements and long-term climate models required recalibration to account for the new baseline. Legal implications arose. Coastal boundaries, often defined by mean high tide lines, could shift with land elevation. While changes were subtle, questions emerged about how law should adapt to dynamic coastlines. The USGS continued meticulous monitoring. Sensors, buoys, and GPS units ensured data integrity, establishing a new baseline for future tectonic events. Accurate records were essential for interpreting ongoing or subsequent shifts. The event underscored the complexity of California's tectonics. Forces shaping the coastline extended beyond visible faults driven by interconnected geological, hydrological, and mantle processes beneath the surface. Researchers specializing in crustal magnetism detected subtle shifts in magnetic signatures along uplifted regions. Rocks deep beneath the surface had likely changed orientation, providing evidence of deep structural movement rather than surface faulting. Sedimentologists observed longshore drift and sandbar changes. Altered seafloor geometry influenced sediment transport, creating slightly more pronounced bars in some areas and thinning deposits in others, highlighting the quiet influence of the uplift. Marine ecologists monitored behavioral shifts. Kelp forests adjusted to new seabed contours, while marine mammals modified feeding patterns in response to altered depth ranges. Even modest tectonic events ripple through ecosystems in nuanced ways. The USGS Red Alert had sparked a global conversation. Researchers, policymakers, and residents alike now understood that California's tectonic margin remained capable of surprises, that the Earth still operated on its own terms. The uplift, while subtle in immediate effect, expanded the understanding of what is possible along this well-studied coast.